Okay, in the last video, we talked about using VSEPR theory, valence shell electron pair repulsion theory, to predict the shape of molecules where there's a central atom covalently bonded to other atoms. So let's go through a few examples here. So let me share the whiteboard here. So the first example was ammonium, and we already looked at that previously, the Lewis structure. So we have to draw the Lewis structure of some of these examples. Let's draw the Lewis structure. So if we have ammonium, so if you recall a few videos back, I don't want this color. So let's look at the ammonium ion as an example. So this is a polyatomic cation. So if we draw the Lewis structure, so if there's 4 groups, no lone pairs, so the electronic geometry is tetrahedral. And the molecular, the positions of the atoms themselves, or the nuclei, is linear, or is tetrahedral too. Okay, so we're going to do an example of another molecule to get the geometry about the central atom. So let's so we're going to pick acetic acid, and if we draw the Lewis structure, okay, and I'll let you, as an exercise, I'll let you. So here's the Lewis structure for acetic acid. So remember, if you have, okay, so on this, let's do for each atom. Hydrogens, of course, are a single bond. There's only one bond between a hydrogen and another atom here. So that by default's a linear, hydrogen's always a linear geometry. Well, it's linear when it's bonded to the bond, the hydrogen-oxygen bond, you know, two atoms define a line. So by default, it's linear. How about the oxygen? Well, there's 2 lone pairs plus 2 bonded electron pairs. So there's a total of 4 electron groups. So if there's a total of 4 electron groups, then the electron geometry is tetrahedral. But there's 2 covalent bonds, 2 nuclei that are bonded, a carbon and a hydrogen are bonded two covalent bonds about the central atom. So, so that means if there's two atoms bonded or two covalent bonds, there's two bonded, okay, two bonded atoms about the central oxygen atom. So that means that the molecular geometry, so the molecular geometry, let's put this electronic geometry, and then this is the molecular, because of the two covalent bonds, is angular. Okay, so now this carbon atom here, there's three bonded groups, no lone pairs. So the geometry, the electronic and trigonal geometry, the electronic and molecular geometry are trigonal planar. Okay. Also, this oxygen has 3 electron groups, 2 lone pairs and a bonded pair. So this is also trigonal. And then this carbon, it's actually, the electronic geometry is actually trigonal and the geometry is trigonal. This one, you have a 4 single bonds or 4 electron groups, no lone pairs, tetra. Okay, so there's another example of the geometry about a central atom using VSEPR theory for the atoms in acetic acid. Okay, so now we're going to talk about polarity of covalent compounds. So polarity of a molecule plays an important role in determining both its physical and chemical properties. So the basic rule of deciding whether an organic compound is polar or nonpolar, and polar basically means a separation, an overall net separation of charge on the molecule. One part of the molecule has a negative charge and then one has a positive charge. So to give you some examples, things like water are a polar molecule, and things like methane or ethane or some hydrocarbons are nonpolar. So to determine the net polarity of a molecule, we need to know 2 things. We need to know the dipole moments of the individual dipoles, of the individual bonds. Remember, a dipole is a charge, a partial charge on 2 atoms separated by a covalent bond where one has a net positive charge and the other has a net negative charge. The other thing we need to know is the molecular geometry, and that we can get using the VSEPR, the valence shell electron pair repulsion theory, or the VSEPR theory that we saw in the previous slide. So to take a linear molecule like carbon dioxide, 2 covalent bonds about the central atom. The difference in electronegativity is greater than 0.5 between carbon and oxygen. Oxygen is more electronegative. So the dipole moment from the positively or the partial positively charged carbon to the oxygen points to the right of the molecule along the linear axis of the molecule. But there's an equal and opposite dipole moment in the opposite direction, 180 degrees apart from the first one. And then what we have to do to get the net overall dipole moment for the molecule is we take the vector sum of the individual dipole moments of the bond. And because they're in opposite directions, they pull equally in opposite directions. The net polarity of carbon dioxide is 0. Okay, so again, here's a net electrostatic electron density, a color-coded electron density map or surface for the molecule. and we see red means a slight excess of positive charge, blue, or negative charge, excuse me, and blue is a positive charge on the iron. So the negative charge in this direction pulls is equal and opposite to this direction. So the net polarity of carbon dioxide is 0. Now water molecule, we know that that has to be a polar molecule. So the individual, there's 2 covalent bonds. So the individual, this bond here, you have a net dipole moment pointing from the hydrogen to the oxygen, and where hydrogen is the more electropositive atom in this bond, oxygen is more electronegative, but you have another dipole moment pointing in this direction towards the oxygen too, but it's coming from the opposite way. That's also a dipole moment. So what you do, if you take the vector sum of the dipole moment, it's vertical like this, but there's a net, this is a net dipole moment. The individual bond dipole moments do not cancel. So, oxygen is, or water is in fact a polar molecule because it has this net overall dipole moment. The same situation, a similar situation with ammonia. Each of the 3 covalent bonds dipole moments about the bond, that points upward vertically if the ammonia molecule is oriented in this manner. So remember, if you want to depict a 3-dimensional shape, like for the ammonia, it has a pyramidal shape. The electron geometry, it has 4 electron groups. So the electron geometry is tetrahedral. So, so ammonia is a polar molecule, okay? Now, if we take some other examples, chloromethane, for example. So chloromethane, remember the hydrogen-carbon bonds, there's the difference in electronegativity between the individual atoms, carbon and hydrogen, it's less than 0.5, so it's considered nonpolar. But there's a net dipole moment along the carbon-chlorine bond because the chlorine shows a net, the difference in electronegativity between chlorine and carbon is greater than 0.5. So chloromethane is considered a polar molecule with a net dipole moment along the, pointing towards the chlorine in the upward direction here from the carbon atom to the chlorine atom. And here's an electron density surface, so you have a net negative charge buildup. So whenever you have a surface like this and the red and blue are separated in one direction, then that indicates a polar molecule. For formaldehyde, we can apply similar reasoning. We have the carbon-hydrogen bonds don't contribute to the overall polarity, but the carbon-oxygen does because of the difference in electronegativity. So again, we have a net dipole moment pointing along the carbon-oxygen bond axis. For acetylene, the individual bond dipole moment, there's not a big difference in the electronegativities between carbon and hydrogen. So this overall molecule is, acetylene is non-polar.